This video was produced by
But I guess we'll go ahead and just get right into it. My name is Kenny Howell. I work as the Facility and Logistics Coordinator for the Virginia Center for Wind Energy. Just a little background, I graduated from here at JMU in 2009 in the Integrated Science and Technology major, studying energy and environmental science. My presentations that I'm going to get a little more into the technical side of wind, talk a little about starting off with the inherent power in wind, and then going a little bit into some basic wind turbine technology. I'll just preface this where I'm not a meteorologist and I am not an engineer, so I won't be getting into the nitty gritty details about wind flow or the engineering behind them. But over my past 3.5 years of experience, I hope to impart some useful knowledge to get some just the general understanding of how these machines work and how we get energy from them. So with that, I'll just go ahead and start. Just starting to talk about a little bit about wind in general. Wind is, actually solar energy, like most other pretty much all forms of energy on the planet. It inherently comes from the sun, and wind's generated through the heating and cooling of the atmosphere, as well as the actual rotation of the Earth. All those factors create this flow of gases on the large scale, and other factors on the small scale due to those. And we really classify winds in about three different factors, talking about global scale winds, regional winds, and then mesoscale or local wind climates. And the global winds are in the widest, the largest sectors. These are the ones that have a lot to do, or you compromise the terms. We talk of like easterlies and westerlies. And these form these vertical and horizontal cycles you see in the images there from the heating and cooling creates these basically cyclical areas along the planet. And these are usually the highest up and the furthest up in the atmosphere. Next is the regional scale winds, which is basically represents air masses that basically take on the characteristics of the land or the sea that they are above. So warmer areas of the planet, you'll get a warmer air mass, like you can see down in the like southern U.S. warmer air masses, and in between these air masses, and as they heat and cool and as they move around in between these air masses, we get the jet streams. And the ones that and this is just an image showing about how the location of a jet stream can change throughout the year as these air masses heat and cool. But the ones that we focus on a lot more, especially with wind energy and especially with small wind energy, are local winds. And these are the winds that are highly influenced by the local geographic features. And the two most notable and common ones to talk about would be such as lake and sea breezes, where basically you get the temperature difference between the land and the water. The land heats and cools to a greater degree than the water does. So as the land heats, you get higher temperature rises, and then pressure moves it out over the sea, causing the lower pressure winds to basically come in from the water over the land. So you often get in the mornings and during the day that flow of air from the water onto the land, and at night basically reverses as the land cools. And very predictable type of wind flow. It's why putting around lakes, breezes, shores is a very reliable source to get. And a similar one, more applicable to this region, is the things called mountain and valley breezes. Very similar effect with the heating and the cooling. The mountains in the valley heat and cool at different areas, which causes flow up the mountains out of the valley during the morning and during the day as they heat, and then down the mountains and down through the valley during the night as it cools. And another thing that's to note with the mountain valley breezes that is often you get especially a lot of people talking about the wind flowing through in between the mountains. They get a really steady breeze because they're located at some place in the mountain, and those are harder to predict. And it's really hard to tell where that's exactly happening without taking some measurements. But basically, it is something that happens. It's basically just an example of the Bernoulli principle. You know, in order for the flow of the wind to maintain the certain energy, as the pressure decreases as it goes through the confined space of the valley, the speed increases. And as you'll show you in a moment, the speed of the wind is pretty much the most important factor when it comes to determining how much power we're going to get out of it. So just as a reference, because I know that these two terms, especially when we're talking about energy and power, can get interchanged a lot unintentionally, is that power is essentially a reference to the potential output of a device, and that's measured in kilowatts, whereas energy is a reference to the output of the device over a series of time in and then we talk about that in kilowatt hours. So this equation here that you see on the screen is essentially the equation that we use to determine how much power is in the wind, how much power that we get out of wind in any given time. And the most important units in this equation that factor in are basically the air density, the area, which is describing the area of our rotor diameter of our turbine, and then the actual wind speed. So air density can change with air temperature, it can change with pressure, it can change with humidity, but the changes are usually not that drastic. This is just something to note. Usually the air temperature or the air density is not going to have a drastic effect on the power output in that equation. You will see differences. If you're in a higher altitude, you will likely get a less lower output than if you put the same turbine somewhere at sea level, because the air is just less dense. But it's usually not very significant, but it's just something to note. The area of the rotor, as you heard mentioned in previous presentations briefly, is a very important factor when it comes to wind turbines. That's essentially the area is proportional to the power that's available in wind. The larger your rotor diameter, essentially you have a larger swept area. The wind turbine's got more area in which it's able to capture the oncoming wind. So essentially by increasing the area, the rotor diameter, you're increasing the available power coming to your turbine by a factor of 2. But the most important part of that whole equation is that v to the third. And it's essentially saying that wind speed increases, as wind speed increases, the power in the wind increases by a factor of 3. It's a cubic relationship. So just to give an example to kind of drive that point home in this consideration of two sites, one with a wind speed of 10 miles per hour and another site with a speed of 12 miles per hour. It's only a 20% increase in the wind speed between the two sites, but that constitutes a 73% increase in those power between those two sites. So what this really, the point of all this is really to say is that wind speed is essentially the most important factor when considering this. And it also means that when you get down post a certain point, really low wind speeds just do not inherently have a lot of power available. It's not that, so you'll see a lot of wind turbines, especially small wind turbines, advertise that they're able to start up in low wind speeds. Some even advertise as low as 1 to 2 miles per hour. And that's all well and good, but there's just not as much. The wind itself does not contain a high level of power at those speeds, and so even though it's spinning, you're probably not getting much power benefit out of it at the time. So usually wind speed, it depends on which size wind turbine you're talking about, whether it's small or large, depending on what you would be considered your ideal wind speed. But usually for small wind turbines, you don't start seeing that ideal crossover into the level. Most small wind turbine manufacturers recommend an average wind speed of around 12 miles per hour if you can get it. But you can still, they're often, especially in Virginia, usually if you can start getting around 9 to 10 is where you're going to start actually seeing some decent power generation. And utility scale is going to be a bit higher than that. They're going to want probably closer to 15, 18. We usually talk about it in meters per second, so Small wind is usually around 4 to 5 meters per second. Large wind would prefer around 7 or 8 meters per second on average, but higher the better in any case, in all cases. And another important factor to consider with wind is that wind speed and therefore the power in wind is affected by height above ground level. This is a graph taken with, we put up meteorological towers as part of, through our anemometer loan program, and this graph was made with data from a 50-meter Met tower out in Tangier Island on the Chesapeake Bay. And it just represents exactly that point. The further you get from ground, basically wind is less affected by obstacles, the boundary layer with the earth, it just becomes less obstructed and it's able to flow more freely. And as the last slide showed, the faster you can get, the more power you're going to get. So ideally, the higher you can get your wind turbine, the more power it's going to be able to see. And another point for looking for that height is that a lot of objects around the ground create a more turbulent wind flow. And as I'll show you in a few slides later, a lot of modern wind turbines operate by using aerodynamic lift. Pretty much the same principle that an airplane uses to fly. And if you've ever been on an airplane, when they've told you you're going to experience a little turbulence, that's essentially what I'm describing here. A wind turbine is going to have the same effects. Wind turbines operate very well if they have a nice, smooth, laminar flow. And turbulent winds, while they'll still be able to capture some of it, it's going to cause rattling on the machinery. It's not going to be able to capture as efficiently. And all that turbulence could possibly cause more wear and tear on your equipment, strain some parts of it, and could possibly lead to more maintenance that has to be done on it down the road. So ideally, you want to avoid these turbulent areas. And the general rule of thumb, and this is mainly something considered for small wind, because usually when you build, people who look at building large wind turbines, you're looking at around 90 meter 80, 90 meter towers, and getting high off the ground isn't really an issue. But for small wind, that can often be an issue, especially in Virginia, where we have a lot of localities that have 35-foot height restrictions on the books. But the general rule of thumb is to try and get the actual turbine, and this is the lowest point where the blade would swing, 20 to 30 feet above a nearest obstruction within 500 feet. And obstructions could be any object, houses, barns, trees, anything. And that's just an image illustrating that turbulent flow. And now I'm going to move into a little more about the wind turbines themselves. These are just a few terms I want to go over to try and differentiate some topics. The industry defines the small wind and large wind by small wind is any turbine that has a nameplate capacity of under 100 kilowatts. Large wind, utility scale wind, is anything above 100 kilowatts. I don't particularly like that definition because I do not think is very appropriate for the small wind description. Because while 100 kilowatts is small compared to a lot of utility scale development, a 100 kilowatt turbine is not really a small wind turbine. That's not something you would likely see outside somebody's house. I like to define small wind by saying anything basically 20 kilowatts and lower. Those are pretty much what you're probably going to see on a residential scale, and 20 kilowatts is even pushing it. Because as you go up in nameplate capacity, as you'll see, as was illustrated in a slide here, this image basically is showing you the rotor diameters of various different turbines. And the biggest circle there is a 100 kilowatt turbine, and that has a 70-foot rotor diameter, whereas your 1 kilowatt turbine at the very, very bottom has an 8.2-foot rotor diameter. So as you go up in nameplate capacity on these turbines, your size grows quite large quite fast. But those definitions are well and good for the industry, but generally in the public, it's not so much focused on that nameplate capacity definition. It's basically taking a look at the turbine and seeing how big is it actually, determining whether they're going to think it's small or whether they're going to think it's large. Net metering essentially is as a policy that a lot of states have now with their utilities, which essentially allow residents or businesses to hook up a renewable energy system to direct to their meter at their house, and basically allow them to feed back onto the grid. How a utility does this is going to vary. Some people will give you power credits for whenever your meter starts turning the other way, whenever you're generating more power than you're producing, they're allowing you to put that power back onto the grid. And like how they handle that is differently. I think a lot of the utilities often give there's this perception that you'll receive a check from the utility for the power that you're generating, but that's usually not the case. It usually comes in the form of like a credit. They'll give you a power credit where essentially you're not getting cash back, but you might not have to pay nearly as much on your next utility bill. I know there's a gentleman in who has I think 10 kilowatts combined of wind and solar down in Stanton Waynesboro area, and I spoke with him not too long ago, and he said that he's probably got between his systems a backlog of about a year's worth of credits. So it's not money he's actually seeing, but as far as actually having to pay for his electric bills, that's pretty much all he can use that savings for. So it really depends on the utility. Every utility will do it a different way. In Virginia, they have a limit on what size of turbine they will allow you to net meter, and that's capped at 20 kilowatts now, I believe. So different states will do it different ways. And the nameplate capacity of a turbine basically decides its rated maximum output. So when I'm talking about when I say a 100 kilowatt turbine or a 20 kilowatt turbine, that's essentially describing if it is able to operate at maximum output, it would be generating 20 kilowatts. And this can be a bit misleading because nameplate capacity doesn't always translate well to production. It's okay, I have a 20 kilowatt turbine, but that doesn't really help me describe how much I'm going to get from that 20 kilowatt turbine. And so nameplate capacity has generally been used as a naming convention for turbines, but there has been debate and discussion on whether that needs to change to more production-based figure. And you heard Mitch use the word capacity factor a few times, and capacity factor and efficiency can often get mixed up. There's some confusion sometimes on what those are and what the difference is. And capacity factor is essentially a ratio of the energy generated by a system or over the potential the system could have generated if it ran at 100% nameplate capacity for the whole time over the period you're talking about. Whereas efficiency is a ratio of the energy generated by a system over the potential the system could have generated if it captured 100% of the available resource at the time. So efficiency would be describing we have this flow of wind, there was the potential to capture so many kilowatt hours of energy from it, but we only captured this percentage of it. That would be efficiency. Where capacity factor would be describing how much you could have generated if you were able to generate at that ideal 100% nameplate capacity for that whole time. So how does it work? The wind turbine essentially captures the kinetic energy in the wind by converting it to mechanical energy via the alternator or generator to usable electricity. And you have efficiency losses through each stage of those conversions. Your highest efficiency loss is going to be from the actual rotor, from the wind making the rotor spin, and that's usually about, that figure might even be a little generous. It's going to vary from turbine to turbine, but typically I would say you could get, depending on the turbine, 30 to 52% loss there, and then you also get some losses through the gearbox, generator, and the converter before it actually becomes electricity, but those are fairly minimal. So all in all, typical efficiencies for turbines and it's going to again be very different between large community and small scale size turbines, but I usually give the figure between anywhere between 20 and 50% depending on the turbine you're talking about. an important thing to note here is the Betz limit, and that is essentially the theoretical maximum amount of kinetic energy that could be captured by a wind turbine from the wind. And that's essentially saying if you got 100% of the energy out of wind, then essentially after the turbine there would be no wind. Essentially the wind would have to stop because you've taken all the energy out of it. But that is essentially theoretically impossible. So the wind slows down after it passes through the turbine, and the 59.3% is that theoretical maximum. A wind turbine will likely never be able, will never be able to reach that limit. It hasn't happened yet. Like, we've gotten some turbines that are a little over 50%, but that 59.3% is very unlikely we'll ever see a turbine become that efficient. So this is a chart basically trying to describe the difference between on-site small wind projects, community projects, and utility projects. So those kilowatt figures in the table are not talking about those aren't a nameplate capacity. That would be like a total installed project size. So residential scale projects are typically 10 kilowatts and under. For a good reference on a 10 kilowatt turbine, that would be the one right out here outside on campus. That is a 10 kilowatt Berge system, and that's probably, in general, most commonly the largest turbine you would see for looking outside of a house. Because once you start getting beyond that, other than the size being possible deterrents for policy and aesthetic reasons in the community, once you start getting much above that size, the cost starts to become a very large factor. But commercials usually have a little bit bigger pockets. We've had wineries in the state that looked at a 250 kilowatt turbine. So I would say 500 and under is probably where you would see a commercial entity looking for an on-site project. Community projects are usually a sort of a unique type of project, and the type of turbine used in those kind of projects can vary. They can be typically they're over 100 kilowatts. We've seen community projects with 50 kilowatt machines, and we've seen community projects with as high as with utility scale machines, like 1.5, 2 megawatt projects. But generally, these projects are not on the scale of a utility-sized project. They're generally smaller. The finances are kept local to try and benefit the community who's working on the project, who's developing the project. So typically, those are probably around the 10 megawatt range, with a little give or take on either end. I would maybe even go as high as saying potential for 20, 25 megawatts. And then the industrial scales and the utility scale projects are usually everything above that, to as low as 30 to 40 megawatts to in the hundreds. And this is just a reference to show you some different sizes of turbines for those kind of projects. You see in the green, the on-site at the bottom pointing to a little imaginary turbine. And that is because the first turbine on this chart is a 50 kilowatt turbine, which is fairly substantial turbine. And most on-site turbines are much, much smaller than that. But as you see, the community scales are typically the first three sizes, and then the utility scale, and then the offshore turbines, which we don't have any here in the U.S. yet, are by far the largest turbines that are in production and in use. And now I'm going to get into little specific characteristics about some turbines. I'll start by describing the difference between a drag and a lift. And this mainly relates to how the turbine captures the wind. And essentially the drag turbines, most relatable one is probably the standard windmill. You see at farms, many blades, captures the wind by essentially just the impact of the drag from the wind hitting the blades and passing through it. And the next to it is a vertical axis machine of a similar design with similar capture concept. And what drag is good for, drag turbines are able to generate a high amount of torque, and that is good for mechanical processes like pumping water and grinding grain and things like that. But as far as electricity generation, it is not quite as beneficial, and that mainly translates to what's called the tip speed ratio, which is essentially the ratio for the tip of the speed the tip of the blade is moving in comparison to the actual wind speed. And the higher the tip speed ratio, the better you're going to get in electricity generation. And for drag turbines, that's typically around a ratio of 1, because the turbine blades can only move as fast as the wind is moving because they are just working off the drag of the wind itself. Whereas a lift turbine, it generates its spins the rotor by capturing aerodynamic lift. Don't need as many blades to do that, and those allows the rotor to achieve a faster speed spinning than the wind speed itself, and you usually see tip speed ratios of around 6 or 7 with lift turbines. So generally, because of that reason, most of the turbines that you see commercially are lift-based. While there are still drag ones out there, they are not nearly as common, and I would say it's pretty much because of that reason. And so a common question is difference between horizontal axis machines and vertical axis machines, and I'm going to try and address both large and small wind as I go through this, because they are very different technologies, and you're going to see a lot more variation in design in the small wind market than you are in the large wind market. But for horizontal axis machines, those are the ones on the left. Those are the ones that you typically see, the big 3-bladed propeller designs. And the characteristics for those are generally, because they're pretty efficient and they're pretty durable. Considered as a proven design because this is essentially the design that the industry has been using for decades. And one of the main design factors that separates them from the vertical axis machine is they require what's called a yaw system, which basically means they can only take the wind from one direction at a time, and that's whatever direction they're facing. So they need a system that is able to orient them into the wind as the wind changes its approach. So usually the yaw system can be either active or passive, and I'll get into a slide on that later, but essentially it's a system at the top of the tower that allows the propellers to rotate into the wind. A vertical axis turbine, I've heard lots of different characteristics about it, and I'm going to try and be unbiased with this. I might get a little on my a soapbox here, but there's a lot of debate out there on vertical axis versus horizontal axis. So I've listed some bullets here of essentially the characteristics of vertical axis that I hear a lot. They're considered more innovative and modern, quieter, less affected by turbulence, can be installed on a roof or a short tower, easy to access electronics and generator, lower cut-in speeds, accepts winds from any direction, and they look cooler. People think they look cooler. And I've highlighted some ones there, and I'll address these as I go down. The innovative and modern argument I would debate, because some of the earliest wind turbines that you can find in history were actually vertical axis machines. I think the first one on record was in Persia as a water pumping device. Vertical axis is not something that has suddenly become a new thing that people haven't thought of before. It's becoming more of something that people are looking into now, but it's not a recent discovery. They are quieter, and that is essentially because noise essentially translates to the length of the blades. A lot of the noise that you'll hear from a wind turbine is coming from the tip of the blade passing through the wind. And the longer a blade you have, the louder, probably the more noise that you're going to get from it. In vertical axis machines, because their rotors are usually pretty contact, that's not really an issue you run into them. So in general, they are a lot quieter than your typical horizontal axis machine. I am not convinced about the less affected by turbulence argument, especially on a lift-generated system, because any turbulent air essentially breaks lift and makes lift less efficient. And I haven't seen a substantial reason or substantial study or report that actually essentially proves this claim. And I don't see how the orientation of the blade will make it any more resistant to a turbulent air than that position of a horizontal axis machine. So I've heard this claim a lot with them, but I just haven't seen any foundational evidence to believe that it's true. A common pro for them is that the electronics and the generators are usually easier to access, and that is pretty true because they are essentially at the bottom of the tower, whereas on a horizontal axis machine they're going to be all the way at the top of the tower. So should there need to be maintenance costs, or assuming the base of the rotor is within reach, these electronics should be easier to access. And I kind of already addressed the lower cut-in speed issue on the previous slide. A lot of them advertise that they can start up in low speeds, and while that may be true, they may start to be able to spin in low speeds. This is not, to me, really a benefit, because if there is very little power in those low speeds in which it starts spinning, you are not getting very much energy out of that. So the benefit of that spinning at low speeds, to me, could almost be counterproductive. A lot of small wind turbines their cut-in speed, which is the speed at which they start operating, on most isn't until about close to 3.5 to 4 meters per second, which is between 7 and 9 miles per hour. And that's because that is the minimum they consider where you might start seeing a suitable power in the wind to actually be worth generating. Since in speeds lower than that, since there's not much power, they usually keep their turbine braked or locked somehow, because if it's spinning and you're not getting any benefit from it, you're essentially just causing wear on the machinery and getting nothing out of it. Except from any wind from any direction. This is true insofar that it doesn't require a yaw mechanism, but at the same time, the way the wind turbine works, one end of that rotor is always going to be coming into the opposing wind. One side is going to be going in the direction of the wind, but the other side is going to be fighting against the wind. And this essentially, whereas because of the horizontal axis machines and because the wind always comes, you're always getting the wind from a specific direction, the flow dynamics and the power production for horizontal axis machines is very, very reliable to do. But with a vertical axis machine, those flow dynamics get a lot more complicated, because it can take wind from any direction, but whether that is a benefit to it or a hindrance to it is debatable. Because if you have one end going with the wind the whole time, but one end coming against the wind, how is that affecting your potential? How is that affecting the efficiency of the machine overall? And so in general, vertical axis machines are generally considered to be a little less efficient than horizontal axis machines. And I will give them that some of them do look pretty cool. You get some pretty cool looking designs with these things. But that essentially is my opinion between the difference between horizontal axis and vertical axis. And one thing I don't have on here that I want to that I should point out is that, like especially on the picture on the far right, that is called a wind spire. Unfortunately, they are a small wind company that is unfortunately now bankrupt. But their rotor is very, very large. And one design issue that comes in with a vertical axis machine right there is you're essentially right in the base on that on the little cylinder there is where the generator is going to be in that machine. And essentially with such a long rotor, you're essentially creating a very long lever at the point of your generator. And when these things start spinning, and especially when they start getting up to rated speeds, you can get it's kind of hard to illustrate, but essentially it'll go in a little bit of a wobble as the rotation because of the centrifugal force related to the spinning. And if you have such a sharp point of leverage down where your mechanics are, you can wind into a lot of issues in that regard. An issue that some vertical axis machines have actually had to build external braces to attach to the top of the machine. You'll see like an arm that comes out around and hooks to the top of the turbine to keep that from happening, to keep it more stable. This was a problem for Windspire, and because they did actually have some early testing done in one of their early designs of their machine by the National Renewable Energy Lab, where they were unable to complete the testing because the turbine mechanics at the base kept breaking. So vertical axis machines can often present a little more design challenges as well. And the image on the left on the vertical axis is I believe it's called a Darius, I believe is how it's pronounced, or a lot of people refer to it as the egg beater turbine. But that was a model for a utility scale vertical axis machine. And I think there was only one or two of them actually built in Europe, but those designs didn't really catch on for the large scale industry, and you don't really see a very large utility scale machines like that. So some of these slides are going to focus a little more on the horizontal axis, because these are features that a horizontal axis will have that vertical axis don't have to worry about. And this one is, you're going to see is basically the difference between upwind and downwind, and this is essentially whether the rotor is located on the front or the back of the turbine. And for utility scale systems, they're pretty much all you're going to see is upwind machines. I don't think I've ever seen a downwind utility scale machine, but I'm sure one has existed at some point. And downwind machines you're typically going to see, if they exist, you're probably going to see them as a small scale wind turbine. And an upwind machine essentially means that the rotor is on the front of in the front of the tower. And this essentially eliminates the potential for tower shading. Your wind is hitting the blades first before going through the tower, so the tower can't affect the wind flow onto the rotor. But as a result, the rotors have to be a lot more rigid. Because when you, especially on the large wind turbines, if you've ever seen one in person, the blades do bend a little bit. They flex in the wind speed. And if you allow them flex too much, they can come back and hit the tower as they spin, and that's obviously a very large problem. So in order to keep that from happening, they have to be a lot more rigidly designed. And all wind turbines have forms of overspeed protection, which I'll cover in a slide in a minute, which basically methods of shutting down should the wind speeds get too high to keep the machinery from getting damaged. And upwind machines can typically do this by furling, which I'll show a slide on later, mechanical braking, electromagnetic braking, or blade pitching. Blade pitching essentially being able to rotate or change the orientation of the blades to break the lift on them so it can't spin anymore. Downwind turbine is essentially the opposite. The rotor's on the back of the blade. This can have an influence in tower shading. Usually the manufacturers that design this try to design it in a way where the tower shading effects are minimal. And while it is present, probably the losses from it are not as noticeable as you might think. One thing I forgot to mention on the upwinds is that as I said before, horizontal axis machines have to have a yaw system to orient themselves in the wind. On upwind, typically on small ones, you have to have something like a tail or some mechanism to keep it oriented in the wind, like a wind vane, so it'll keep in there. And large-scale machines don't have that, and I'll describe how they do that in another slide. But downwind machines don't need that. They keep themselves oriented into the wind, essentially via coning. If you were to look on the side of a downwind machine, the blades are going to be slightly tilted back, essentially forming a very, very gradual cone. And essentially, by that design process, they're able to keep themselves oriented to the wind just based on what direction it's coming from. The problem with this, though, is it presents a construction challenge. That means that once put the tower up, the tower has to be very, very level, because if it's not perfectly flush, you could have the turbine could sag to one side very easily, and that's going to cause a lot of problems for your turbine and how efficiently you're going to be able to get energy from it. But the rotors, because you don't have to worry about them hitting the tower, they can be a lot more flexible. And because they don't have a tail, these downwind machines typically don't exhibit the overbrake protection for furling, which is not on this slide but is coming up. So yaw control, basically the method that keeps itself oriented in the wind. You have active yaw and passive yaw. Active yaw is pretty much what you're going to see on everything larger than a small wind turbine. And that's essentially a yaw mechanism is electronic. It's hooked up to some sort of sensor or a computer that reads where the way the wind is coming. Usually on top of the turbines, you'll usually see wind sensors of some kind. So it can read the wind and orient itself via an electronic process, or it can be done manually by someone on the ground in the power control to power plant. Whereas passive yaw control is usually a engineering design built into the turbine. It's just able to do it itself. It doesn't require any external assistance. There is usually some way, particularly with furling machines, where You can manually furl it with a mechanism if necessary, but usually it's not necessary. It's built into it. The one difference for passive yaw control where you would have an electric input is with the electromagnetic braking system that would be exhibited in the turbine on the far right picture. That's a southwest sky stream. And the way they've designed their tower is that their inverter for their machine is all their electronic components are up in the top of the tower in what's called the nacelle, whereas a lot of other turbines will have the inverter down at the base of the tower. And essentially they utilize in their system with some software assistance in the inverter to for it to monitor, basically back calculate wind speed. It'll look at the energy it's producing, estimate the wind speed it should be seeing from that, and if it calculates that it's too high, it will use the magnets in the generator to put on a brake with some relays, and it will switch that system on and off on its own based on that. But that would still be considered sort of a passive yaw control because you don't actually have a manual way to go in and do that yourself via computer or something like that if you would need to. So, okay, there we go, overspeed protection. So furling is an interesting design mechanism. It's essentially, I don't know how well you can tell from those pictures, but it is essentially a way in which the turbine is designed where the rotor will essentially get turned out of the wind, either vertically or horizontally. Horizontal would be in the picture on the right, vertical would be in the picture on the left. So essentially when you get the horizontal furling is if you have the blade essentially kind of folds to the right and causes the rotor to basically rotate out of the wind, keeping it from catching it at a proper angle, basically stopping it from spinning effectively. And vertical is essentially the opposite. Instead of rotating to the side, it will essentially rotate, fall back like that. I haven't seen too many vertical designs before. I know they've existed. Southwest, the people who make the Skystream used to have a vertical furling turbine. And they said a major problem that they ran into that was in wind speeds that were right on the verge of where the furling would engage and go on and off. They would have problems where it would go up and then it would slam back down and kind of cause a jarring every time it would go up and down, and that caused them some maintenance issues on that machine, which, as far as I know, they have worked out on that system, but is a potential engineering issue, that one of the engineering issues you can run into with that. Another common one is blade pitching, which, as I mentioned briefly before, is essentially some sort of mechanical method for switching the angle of attack the wind has on the blades to break the lift. And if it's a lift turbine and it can't catch the lift, it's not going to spin. On smaller machines, this is usually done in some sort of passive way. The one on the left, you couldn't find a suitable picture for it, but essentially those blades will fold back, basically close when the wind gets too fast, and that closing action will change that angle of attack and slow the rotor as necessary for that machine. The picture in the middle, I don't know if you can see it too well, but in the blade on the right, right here, there are some that are designed where the tip of the blade will be the only part of the system that switches the angle of attack, but it's basically same basic principle, trying to break that lift. And large-scale wind turbines, rather than trying to yaw the whole system out of there, each individual blade has a mechanism in which they can electronically rotate those large blades and shut them down that way. As one of the more efficient ways of actually shutting them down and keeping them from spinning. And then other methods are the electromagnetic and mechanical braking. Mechanical braking you don't really see as much because it requires more parts and can lead to more maintenance wear and tear. So they usually go for other methods than that if they can avoid it, and mechanical braking being there if there's a necessary fail-safe of some kind required. A common question that we run into is, why do you normally see wind turbines with 3 blades? It's mostly an engineering reason. I'll start. You do see large-scale and small-scale 2-bladed machines. Those still exist. And that's because they're generally cheaper. So less materials means less you have to spend to make them. And when you're talking about a 80-meter blade or so that can be a significant cost to not have to spend. One of the issues that I'll get into later on is may have heard the term shadow flickering, essentially shadow from the blades if the sun is behind a wind turbine. Less blades means this is going to happen less frequently. Lower noise because there's less blades, but the main thing is that it can cause balance issues. And that has to do when, especially on large-scale machines, when you have hundreds foot of rotor diameter. If you have one blade at the that's think of them as the vertical position where one is pointing up and one is pointing down. The blade that's pointing down is going to be experiencing much slower wind speed than the one that's pointing up. And you're going to essentially get kind of a tilt on that. And that difference in balance can cause a lot of strain on your machinery and the nacelle. And same issue can happen when they're both horizontal and you're looking at yawing the turbine. You can't really yaw it as safely that way because those blades are going to pick up issues and can possibly cause damage to the machinery on the inside. There are ways to avoid things like that, but it's consideration, and some manufacturers and companies just don't prefer not to deal with that. You won't really see a large-scale machine with any more than 3 blades, and I think that probably has primarily to do with a cost issue as well as a weight issue. But on small-scale machines, you can find some that have more than 3 blades, but typically they will still be odd numbered, so like 3, 5. I don't think I've actually seen any more than 5. But having more blades essentially means you can have more opportunity to catch lift. You can it can possibly get the rotor to spin faster. An odd number of blades is essentially going to balance the rotor better, and that has to do with that issue with the top and the bottom blade. So on a 3-bladed system, for example, when one of your blades is pointing at its highest, you have 2 blades at the bottom catching the lower wind speed, and that helps to keep that angle from getting too extreme and helps keep it balanced to keep the machinery from causing issues. A con to this is, as I said, more blades means you're going to have to spend more. If you have too many blades, you can possibly catch wake effects, which essentially means is that once the wind passes past one of the blades, the wind behind the blade is going to be slower and more turbulent. And if you have blades that are too close together, that effect, you don't want the wake effect from one blade to start affecting the blade that's following it. And that can cause them lower efficiency if they're too close together. And more blades means they're heavier, and the heavier rotor means that you're going to need more energy to actually spin that rotor. So the 3-blade design is essentially a compromise of all those factors and considered to be the best trade-off for what you get as far as money and efficiency and balance. It's essentially a compromise of all those factors. So these are just some examples of different systems. So to get a perspective of where you might see these are just on-site systems. One you would see at a house, a 1 kilowatt Berge system, probably one of the smaller ones you can get, and a 20 kilowatt in Ireland, 60-foot tower. These are obviously in places that are populated, not near buildings, cars. They're big, but no, not humongous. And community wind systems, sort of similar, but the next stage up. These are often the systems that you're going to see maybe only 1, 2, 3 turbines at most, generally still only 1, but are generally quite a bit larger because they're looking at using the electricity for more than just one building. So these are just some examples of those, of a 100 kilowatt system in Massachusetts and a 50 kilowatt system in Vermont. And another example of a community wind system in Hull, Massachusetts, 660 kilowatt machine, and that's next to the town's high school, actually. That building right next to it is actually a high school. And then the standard utility scale systems, these are the ones in the wind farms. You're going to see large quantities, generally out away from some distance from a population center. They might be nearby in a few miles, but they're not going to be built up around and near buildings. This is one that you can see off of Pennsylvania Turnpike. A good example of one that you might see in this area, proposed mountain kind of project. But typically you'll see them the ones out in the Midwest, big open flat fields of white towers. And then hopefully in the future, but already existing in Europe, you'll also see these in farms out in the water. And that's the end of my initial turbine introduction. I had scheduled break after this if people need a break, but if anyone's got any questions.
Yeah. What size turbines do you see offshore? You know?
Offshore, it's usually, Dane, you're the expert on this, you would say it's usually 2 megawatt and up, right?
Yes, between 2 and 5 megawatts.
There's not really much bigger than a 5 megawatt machine right now, is there?
Not currently deployed offshore, but they're looking at, they're always trying to develop for larger turbines offshore.
Okay. Yeah.
You spoke about the area to velocity rate issues in power generation. I know Venturis have been one response to that. What about for example, Tesla-style Venturi systems? Tesla turbine?
I'm not sure I'm familiar.
Catches the wind and spirals it into a small turbine. I know such a system was proposed at Cape Charles, for example.
Oh, okay. I think I know what you're talking about. I know that there are some companies that are researching those techniques, but I think that's pretty much the stage that they're in right now. I haven't seen any in actual practice or actually up in operation, because I think there's still some question on. It's one of those things I think in theoretically, they should increase production, but whether, I guess there's still the gray cloud and whether that actually translates to something we're able to actually do in practice. But I have seen several different methods along those lines, but none actually being built and manufactured yet. Yes.
Yeah, I got a couple of questions and a follow-up. Our turbine out here, manufacturer, what size is it? Tower height and wind speed?
Okay, you're talking about the one here on campus? The turbine here on campus is manufactured by a company named Berge. They're probably one of the oldest small wind manufacturers in existence. They've been around for decades, doing it for years. Meaning two things. One, that means their design is fairly well proven and, trusted. The con to that is that it's an old design. They haven't really changed much on it in the last 30 years. It's pretty basic standard design. So newer manufacturers would debate that might be Berge's downfall, is that they haven't really innovated on their design very much. But Berge seems to have sort of the standpoint, if it's not broke, why fix it? It works well for what it is. It is on a 120-foot tower, which is probably around the ideal height. Between 100 and 120 feet is where you want to try and get a small wind turbine if you can. It's not always easy, mostly due to policy and local issues, not mechanical issues. But the wind speed here is very, very low at site on campus. I don't think I can quote you a number right now. I could give you, it is less than the ideal, so it is not up at that 10 and 12, and we knew that we knew that going into this facility, and that's just one of the unfortunate circumstances of where we're located. This is not the windiest area. We're not up in the hills anywhere, but we do see winds that will have some sort of generate electricity. But our main intention for this facility is for where that is going to be more of the training aspect and the types of testing that we're able to do with our modest wind speed. But we knew going into it that we're probably not going to see a significant amount of electricity generation from that unit at its location. If I was putting this in it, if my house was here, I would not have put in a system like that.
Size? Is it 10 kW?
It is actually a 7.5 kilowatt system. The external is the same as the Berge 10 kilowatt system, but the internal is downrated to a 7.5 kilowatt generator. And my understanding for that is because their 7.5 kilowatt system is used for more of the battery charging applications, which we're doing in the building at that facility, whereas their 10 kilowatt system is designed more for grid integration and net metering.
Are we feeding that back into the university, or is it being spun off?
It's fed back in.
Yeah.
When we actually have enough
Okay,
to feed
to
it.
follow up, if I may, I'm going to challenge you on your horizontal versus vertical.
Okay.
You made a minor point of the operation and maintenance, which I feel is a major point. Lubrication, parts wear out, the problems with the thing constantly turning and how it connects to the rotor, those wear out. From a mechanic side, I like everything on the bottom. And the back side of the horizontal does have a drag on it because it's pushing against the wind as it's moving. So that should not be discounted the way you said that the other one turns into.
That is a good point. That is something I didn't mention. There is a characteristic of horizontal axis machines that I think it's usually described as yaw error, where factors like that are interrelated, where you will get issues, whether it's slowing or inefficiencies due to the wind having, especially if it's in an area where the wind direction is changing a lot and that has to move. It doesn't just automatically whip over and line up with the wind. It takes a little bit of time for it to get over there. And you will get efficiency losses, and that will vary depending on how fast the wind speed changes, the tail, the machinery. There's a lot of factors that can go into that. Usually it's not very much, but it does exist. Is that kind of the area you're addressing?
Yeah, and particularly the maintenance. If you put the windmill up and you leave it behind, but fine, then the mechanic's got to deal with it. If it's 120 feet in the air, it's a lot more difficult to lubricate the machine than it's on the bottom, or any form of maintenance. And like I spoke with the previous gentleman, there's a very heated debate going on LinkedIn about maintenance and quality of the units and that sort of stuff, and it's bringing it really to the forefront. It's nice we put it up, it's great windmills. How do we take care of them? So I think that should be a more emphasized factor.
Do you have a question?
Yeah, I'm sorry, I didn't know my question. But my question is on the residential side. Who are the top three that are penetrating the market right now?
As far as manufacturers of turbines, probably Berge is near the top. These are in no specific ranked order. I would say Berge and Southwest Wind Power are probably two of the top ones. Followed shortly behind probably Endurance Wind Power, Gaia. Those would probably be my top four as far as ones that you're likely to see. Most of the wind turbines, Virginia had a rebate program not too long ago for small wind systems, and of all of the machines that were installed, the two most frequent that were installed were the Southwest Skystream and the Windspire.
Does Virginia have any idea how many of those were installed?
Through the rebate program, there were 27 projects that were successfully completed. Yes.
All right. One other question. You were dealing with vibration issues on comparing the vertical versus horizontal. For your typical case windmills, which I guess are probably going to be horizontal axis, what kind of foundations do you need to prepare for?
Well, that'll depend on a couple factors. Of course, the manufacturer, which kind of tower you're using, and what kind of land you're putting it on. But it's typically just a standard concrete foundation, a mat or a pier foundation, and then the thickness and the depth will vary depending on what kind of soil you're having to deal with. But to my knowledge, it's pretty standard pier mat foundation. I know that the Southwest Skystream, for their unit, has developed a specific foundation for theirs that they call the Smart Foundation, which is one that is designed specifically for their units. But I think they're one of the few, if the only manufacturer I've heard of actually doing that. And usually a typical contractor who's, does foundation work can usually do foundations for these systems as long as they're familiar with doing tower foundations. You just need to get someone to get you the proper dimensions, and that's usually a combination of working with the contractor as well as the tower manufacturer. Okay, and if you guys want, we can take a short break here, and then we'll start back up in about 5-10 minutes. That work? We're almost done. Just got 2 final quick sections to go. Myself and my colleague Dane here are going to present a little bit on some siting and some other considerations beyond the technical aspect, and then our interns Blaine and Chris are going to focus a little more on what's going on with wind in Virginia. Let's get back into it. So here is a general outline, very, very general, of what you could expect as a outline for a wind project development. And this is definitely going to differ from small to large scale. This is more of a utility or community kind of outline, where you'll go through a prospecting phase, early preliminary analysis. Companies are going to figure out where can they put a wind turbine, what places look good for various different aspects, have nearby transmission, good wind resource, all those factors. And then they'll basically either start putting in their bids or get in the queue, and in the case of offshore, offshore is a little different because the spaces where you can develop offshore are kind of already pre-chosen in what are called lease blocks, and I guess those are set up by the federal government or federal and state governments. And they're basically those blocks that basically saying, here's the spots that will allow you to develop an offshore wind farm, and then they will put out bids for those spots. Whereas for onshore, it's kind of, I guess for lack of a better term, a crapshoot. You'll look and see where it's good and then identify the barriers later. And then you get into the planning phase where you start going through project proposals, going through the permitting, your environmental assessments, your wind resource assessments, your financial planning, project layouts, where you're going to put the turbines, how you're going to lay them out, working with your interconnection agreements with the utilities, and all the time in this phase will differ depending on the scale of the project. I have here saying 1 to 5 years. If you're working on like a small scale project for your house, it could be months or weeks in this planning phase, depending on how much information you have going into it and how much work you have to put in to get the permit. But usually, typically in large scale projects, you could be looking at a 3+ year planning phase. This is the longest part of the wind project development, because this is where you're going to find all the hurdles that you run into if you have to do, because a lot of the assessments you have to do, you need time to do them. Typical wind resource assessment for a large scale wind developer likes to get 3 years worth of wind data before they'll start doing their analysis to determine what it's like, because they want to get that multi-year variability, because winds change from year to year, from season to season. So they want to get some averaging going on, and then they'll go back and compare that to archive data and so on and so forth. And on environmental assessments as well, and the interconnection agreements you saw on the other presentations, the queue, you could have to wait a long time sometimes before you can actually get to your point where the utility is going to work with you. And then when you actually get to the construction phase, that's essentially the easy part. That usually can get that done in a year or maybe a couple years depending on the size of your project. But once you're actually able to start the construction, the longest part is getting to the point where they'll actually let you start the construction. And then you have the operations and maintenance of the facility while it's up and running. And then at the end of the life cycle, which is generally estimated between 20 and 30 years for average wind turbine, you could have the choice of either dismantling your equipment or refurbishing the equipment. We're like taking down a wind turbine and putting up newer technology in its spot. A lot of wind turbines and a lot of large-scale ordinances will require, when you're developing a wind farm in an area, to have some sort of decommissioning plan. Like, once this has run its course, what are you going to do to the area? They want some sort of promise of some sort of mitigation to help refurbish the area if there was issues, taking out, some going as far as like requiring taking out the concrete foundations and, you know, some sort of effort to get any habitat that may have been disturbed put back into place. So here's some common things about what you consider when you're trying to site a wind turbine or a wind facility. Wind resource is obviously going to be one of the most important ones because that's what you're getting your energy from. The current land use, environmental impacts, what government regulations exist, how much is it going to cost you, and that takes into factors including the distance to your nearest transmission source, distance to your nearest load, road access, and all of the financial issues like such as the PTC that Mitch and Dr. Miles explained in the previous two presentations. What kind of payback that's going to allow you, what's the community's opinion you're working with, or do you have a lot of opposition, or do you have a lot of support? A big issue with that comes into the form of aesthetics and noise and flicker issues, how much room do you have to space the turbines, how many are you going to put? Lots of factors go into these considerations on picking where developers want to put wind facilities. And you may have heard in the previous presentations they mentioned something about wind classes, and that's essentially just a form to describe the quality of the wind resource. And these classes are based off of the wind maps that you were shown earlier. And essentially, basically you take a class, and the class breakdown is right here. Essentially, describes a wind speed range, and here's the breakdown. Really, what class 1 and 2 is where you're going to see it start being marginally good for small wind production, closer to a class 2. Class 1, I would say, is a bit iffy, but generally if you're at least to have class 2 wind resources, you can get some form of decent small wind production. And class 3 is, I mean, where you want to be if you can. But that's where it starts becoming marginal for community scale projects, but is still generally unsuitable for large scale utility projects. And then 4 and up is where you'll start seeing more interest in utility development. Now this might be changing as technology increases. You've heard a lot of talk about increase in rotor diameters in blades and turbines now starting to be able to help function lower wind speeds. This means that in the near future we might be seeing large wind farm developers looking in areas such as that have marginal winds, like a class 3 wind resource, because advances in the technology are allowing us to actually capture better energy from those wind speeds with larger rotor diameters. But that is on the verge, as still probably most of the development is going to be, you're going to see, is going to be class 4 and up. So how do they find their wind resource? And there's several different methods they can find this, especially large scale developers. They want hard data. So what they will do is they will put up a meteorological tower, what is you've seen in this picture right here. It's this part shooting off this way. And they essentially outfit this with the with sensors that you see on the left, and more than just these, but that's a basic anemometer that measures wind speed and a wind vane that measures wind direction. They'll put a series on these of anywhere to a 50 meter to a 80 meter tower. 80 meter is usually the ones the large scale developers put up now, and they'll put those out their site for ideally 3 years and just start taking data and then analyze the data as it comes in to profile the wind resource that they're looking at harnessing. Some other methods to do the same thing, as you might imagine, putting up an 80-foot temporary tower is not an easy task. So there's 2 new technologies. This picture right here is a SODAR unit, and the one below it is a LiDAR unit. These are new remote sensing devices that have come out, and they basically, the top one is able to measure wind speed and direction data via sound waves, and the LiDAR basically using a laser. And the benefit of these is that these units are much smaller than an 80-foot tower. This is you can't really tell from the picture, but the SODAR unit is about as tall as me, maybe a little taller. It's just a big box, and the LiDARs are even smaller, little bigger than maybe a briefcase, depending on which one you're using. The difference between the two is they're both designed for the same purpose, remote sensing. SODAR is considered to possibly be a little less accurate, but is a lot easier to use because it doesn't require as much power to operate. And when you're talking about putting this piece of equipment out in a remote area, that's a very important factor. How are you going to keep it powered? That can really be powered off of nothing more than a couple solar panels that they equip with the device. Whereas the LiDAR is a much larger power draw, and that usually you have to look at some form of generator to go along with that. And LiDARs are obviously generally a lot more expensive than a SODAR unit. Typical price for a SODAR unit, I think we've looked at in the past, is between $30,000 and $50,000, whereas a LiDAR can extend to a couple $100,000. So that is also a very large factor. And other places, other than taking your own data, this is usually putting up a Met tower using one of these devices is not very practical for small wind projects. So usually a lot more general methods will be used for siting those. They'll focus a lot more on archived wind data if they can find it. If you can usually get suitable data enough from even a home weather station. Lots of other sources. We offer a program, some states offer anemometer loan programs where people can apply and get one of these towers put up if they're interested in taking the data. But a lot of small wind installers and a lot of the small wind industry doesn't focus as much on that data collection part. Now, I believe some data is better than no data, because data is wind is very intangible when it comes to determining whether or not you're seeing energy enough that's going to generate energy. And the one thing you want to note is because one day you might be getting really, really fast, nice, gusty winds, and the next day it could be completely dead. What you need, data helps you find out, is what you need to make wind energy profitable is you need to know an average annual wind speed. Like over the year of a typical seasonal variation, are you going to see enough wind during the year to make this profitable for you? And you might get some really gusty days, but if they don't happen frequent enough, you might not be getting the energy that you think you could be getting from the turbine. So the small wind market is a little harder to sort this out. Did you have a question?
I do. Are the SODAR and LiDAR then at ground level and they just profile up at whatever it is, 80 feet or wherever you want to capture the data?
SODAR and LiDARs, actually, they are at ground level. They actually, one of the other benefits of them beyond the towers is that they are both able to extend upwards to 150 to 200 meters in their measurements. The caveat with that is that the higher you go, the lower quality the data is typically, and that's more evident with SODAR than with LiDAR. The way SODAR and LiDAR are in the industry right now, they are basically the Met towers are still considered the standard. There are very few companies that are willing to do their prospecting solely based on SODAR and LiDAR measurements. Usually it will take SODAR and LiDAR units and accompany a Met tower to try and get correlation, and they will compare the SODAR or LiDAR data to their Met tower data, and if the comparisons are very, very close between the two at the heights that the measurements the Met tower can get, then they'll have a little more confidence in what they're seeing from the LiDAR or the SODAR. But as of right now, those two technologies have not reached the level where they're considered basically a standalone industry standard. A lot of times they're paired with Met tower installations. But the hope from having to install both, 50-meter Met tower goes up in about 2 to 3 days. SODAR unit goes up in about 2 to 3 hours. So there's a significant difference in significant pro in trying to advance these technologies in as long as they are able to provide the same quality data. So some typical issues that we run into a lot with wind facilities I'm going to cover now that were mentioned briefly in the considerations slide. And a typical one is you hear about a shadow flicker, and it's fairly self-explanatory, and it occurs when moving object becomes between a viewer and the light source, and it creates the recurring shadows. And for a wind turbine, that is basically whenever the wind turbine blades pass in front of the sun. Typically, shadow flicker can be an issue, but it is an easily avoidable issue if sited properly. In general, the shadow flickering is only going to occur during short periods of the day, and this is usually when the sun is low in the horizon in the evening or in the morning, which are both prime times of annoyance, especially if people are trying to relax. But this is one of those things that really proper siting is the easiest way to mitigate this. This is something that can be factored in, that they can measure in their planning, and they should be easily able to avoid dwellings and houses to avoid this issue. Now, this is a problem if new homes or residences are built up of already existing facilities, but new development facilities should easily be able to avoid this kind of issue with proper siting. And the shadow flickering is also going to be very focused and probably occur to very specific people, because whether you're seeing the shadow flicker or not depends on where you are in relation to the turbine. So you have to, the sun actually has to, you have to be in, the turbine has to be between the viewer and the sun. So not everyone in the same area may be experiencing the shadow flicker. It could be possible that it might be only a couple houses, if at all. But this is something that developers can be an issue, and it can be a very obvious nuisance, but a responsible developer should be factoring into this their planning. It should be very easily manageable and avoidable. It's important to note that this is a significant difference between shadow flickering with a large wind turbine and with a small wind turbine, and this is mainly due to the fact that small wind turbines are, first off, a lot shorter, and it's going to be a lot more difficult. The shadows for these small wind turbines are not going to stretch nearly as far as they would for a large wind turbine, and it's the period that you're going to see the sun, perspective you're going to be able to see the sun behind these machines is a lot shallower angle, but it's still a consideration you'll have to do, especially if you're putting one up at your house and you have neighbors and that's a concern. It's something you want to look into, but generally the concern is a lot less. And also it's less of an issue because of the rotor's faster RPM on the larger ones. Larger turbines, the blades obviously move very, very slowly, and that's mostly a safety issue. You don't want them to move too fast, or it could essentially hurt the machine. But for smaller wind turbines, because they have a much shorter rotor diameters, the blades are able to move a lot faster. And the faster the blades move, perception goes, they start to be less perceived as individual blades and more as a rotating disc, depending on how fast it's going. And usually when it gets up to operating speeds, you don't really see the flickering effect as much as you do just a solid circular shadow. It depends on how fast the blades are spinning, of course, but typically flickering with small wind turbines is not nearly the issue it is with utility scale machines. Noise is another one you hear commonly about, and two factors you have to consider when you're thinking about noise in wind turbine is things called ambient noise and intrusive noise. And ambient noise describes the combined noise from all sources, both near and far, at a given location. And intrusive noise describes any noise that exceeds the level of ambient noise. So now you have the question of what makes the noise intrusive, and that can essentially it's very relative, is the point I'm going to try and drive here. What makes noise intrusive could be the time of the day. Is it noon, or is it 3 in the morning? Is a situational circumstance? Are you trying to sleep? Do you have company over? You don't want noise? And how sensitive are the listener's ears? All of these are factors, and it will vary from person to person and location to location. So noise can be a very difficult aspect of siting wind turbines, especially when you're trying to communicate concerns and answer concerns of the public. Common way of quantifying noise, we use the measurement of decibels. And on the decibel scale, I've tried to describe it here. The way it's listed, you have an image of some common decibel readings and noises associated along that scale. But a noise that is 10 times as intense as a 0 decibel reading is labeled as 10 decibels. A noise that is 100 times as intense as 0 decibels is 20 decibels, and 1,000 as 30, and so on and so forth. So the scale describes the intensity of the sound in that regard. And typically, a turbine standing at the base, and this will vary between large and small turbines, but typically between the two is between 40 and 55 decibels on average, which is, I think, generally associated as comparable to a conversation normal speaking volume. Or a hum of a refrigerator in your house. The noise from a turbine emanates pretty much specifically from the blades, as I mentioned before, from the tips of the blades cutting through the air, and the faster it goes, the louder it's going to be. Large wind turbines, as you know, as I mentioned, move very, very slowly, but they have very, very long blades. So although they appear to be moving very slowly, the speed at the very tip of that blade is very, very fast. But it's typically not a noise that you can hear from very far away. If you're standing right under the turbine, it's something that's noticeable, but still it's not very obtrusive. And this is coming from someone who's visited a wind farm. If you haven't visited a wind farm, I think that's really the only way to really get a good grasp on this, because I can communicate to you that, oh, it sounds like a conversation, but the only real way to relate about it, and if you're really concerned about it, I would recommend go try and see a wind farm or go find someone with a small wind turbine and just listen for yourself. But typically a lawnmower, your neighbor mowing their lawn, is going to be louder than a wind turbine out in your backyard. But it is still a concern that you want to address. This is not something I'm trying to gloss over as not a concern, because whatever someone considers intrusive is highly relative, and if they have a valid concern, they don't like the noise, then that's a valid concern. But typically the intensity it's not very intense noise from these machines. Assuming there's no mechanical issues, then that's usually a sign that something's wrong. Birds and bats are typically the wildlife concern that you hear with wind turbines, and wind turbines have been known to kill birds and bats. That is a fact. But it is important to consider the types of birds that are getting impacted. You'll see this graph there is a favorite I think a lot of wind proponents like to use, and they like to use the funny comment of how cats kill more birds than wind turbines do. But what that graph fails to point out is the type of birds that are being impacted. Cats are probably going to be getting these little birds here, the cardinals and your songbirds, whereas the concern with wind turbines is these guys, and your raptors, and your condors, and your big birds. And those are the ones that are typically endangered, those are the ones that are of most concern, and those are the ones that want to be protected. Typically what is believed to happen with wind turbines, it's hard to, a lot of research has gone on in this area. And in existing wind farms, the wind farm that probably caused this issue, brought it to light mostly, was one of the first ones in the U.S. is the California wind farm in Altamont Pass. And one of the issues with that wind farm is a lot of those turbine towers were lattice towers. And if you don't know what a lattice tower is, it's kind of the laddered tower. Lattice tower is the one we have out back. And the problem with those turbines is that they cause a lot of opportunity for nesting. Birds will try and nest in those turbines, and then you have the spinning rotor blades right there. It was also, I believe, in a high flyway area where you get a lot of bird traffic, especially raptor traffic. Other theories is that when these birds hunt, they kind of fly basically in that rotor area, in the area where they're able to get hit. And a theory that I've heard is that when they're hunting, they've kind of got what eagle's vision is going on, and they are really focused on whatever they're diving and attacking, but not so much to what's going on in their periphery, where there's typically not moving objects that they have to worry about. But again, with the birds issue is really another factor of location. You don't want to put these facilities in a migratory flyway. You don't want to put these near nesting areas. You don't want to put them where it's going to be a high probability of impact. But again, it's going to be relative, I think, to every person what they consider to be an impact. Is the impact how many are killed versus the total population? Is it causing the population to go down? Is it having an effect on the population at all? I mean, I know there are some who won't be happy unless nothing is killed. But I mean, I think any man-made structure has the potential to cause some sort of environmental impact on wildlife or habitat, what have you. But this is something that can be mitigated and is a very important concern that is addressed, especially in the development of new wind farms. And I know is very important, especially discussing offshore wind farms, because especially off the coast of Virginia, there's a lot of migratory pathways over the Chesapeake Bay, and that's something that is heavily considered. With bats are a little less understood at this time because it's something that's come out more, especially with development over here on the East Coast. Bats have been found killed due to two different ways. From the last report I read, it was about a 50% killed by impacts, and the others were killed by a process similar. It was described similar as sort of the bends, like as you go scuba diving. As the blades pass, they create a pressure difference, and the pressure difference, if they get caught in it, essentially kills them. And the relationship to bats and wind turbines is still something that's being heavily researched and heavily understood, whereas we don't know if they're not seeing them. There have been some facilities have infrared cameras to try and monitor them. They've caught bats actually following blades in some instances, and they're not sure if it's like one of those things where they see something, they find something moving, and they're trying to figure out what it is. But there's a lot of research going on in that area to try and figure out exactly what the interaction between wind turbines and bats. Yes?
Coming back to the birds, are there any attributes of the actual turbine besides picking the best spot for actually on the turbine that can help mitigate it? Like, I read somewhere where some turbines, they have a perching spot without any safe, it would be in with blades. Have you heard of anything?
I've heard of some various techniques. I mean, there have been some research going on whether painting the blades will make them more visible or not. But then when you get the issue with the painting the blades does then they become more obtrusive for us, for people who don't like seeing them. I think I've talked about some sort of devices that emanate noises. I think this is particularly more on the bats, though, to try and emanate some sort of frequency to help make them avoid it. A lot of it is there are mitigation techniques, but they're mostly more looking towards, I think, the bats than the birds, because the birds, in general, if sighted properly, can pretty easily avoid them. I mean, you can find studies where they've monitored bird migration and bird travel around wind farms and seen that a lot of flocks will go. They recognize that there's something there and will go around the facility. There are other concerns that are indirect impacts that aren't like actual bird kills, but do the wind turbines affect like nesting areas near the birds? I know there was a presentation in Atlanta at the Wind Power Conference that addressed that specifically, and it was trying to quantify indirect impacts on birds for these facilities. And in some instances, what was interesting is they theorized that the wind turbines were actually helping some species, depending on the species, particularly in nesting and breeding, because they were finding in the samples that they chose basically an increase in their bird activity near the facilities. And the theory that they're testing now is why that is, and their theory is that perhaps that the wind turbine facilities are having a effect on the predators of the birds. So the birds are setting up house somewhat near the facilities. And when I say near the facilities, this isn't like right under the turbines. I mean, this is like in the general area of the facility. These are not birds that are generally they were worried about having impact issues with. Well, these were more of the smaller species of birds. The birds in that study were smaller, more comparable to songbird size, not the birds of prey. I don't know. Do you have any input on mitigation? Yeah, I don't know if I'm answering your question well enough. I know that there are. I'm just not well versed on some examples. But another issue with the bats is that bat populations are not understood very well as of right now. It's hard to quantify how many of a specific species of bat exist. Specifically because of the nature of bats and where they live, it's hard to get a good quantification of how many there are of any individual species. So it's harder for people, as compared to birds, to relate whether this number of bats were killed by this turbine, how significant is that to the overall population. And I know that's something that is still being heavily researched and trying to find issues for. But I think the bat issue is of a little more concern at this point in the industry than the bird issue, just because the bats are a little more of a new issue that are having to come up, and the mitigation for that is a lot more important, especially since they seem to be killed by things other than just hitting the turbine itself. But another thing to note is that, again, there is a very large difference between small wind turbines and large wind turbines in this regard. There hasn't been, to my knowledge, an official study of bird impacts of a small wind turbine, but I don't know if that's because it is not a concern, so no one felt they need to research it, or it's just no one's actually spent the time to try and research it. But given the characteristics of the small wind turbine, the shorter towers, smaller rotor diameters, faster spinning blades, they cover a lot less area. They're not going to be in the path of nearly as many birds. They're not tall enough to really affect the birds of prey, the raptors, like the utility turbines are. The birds that would be affected would probably be the songbirds, especially if you're talking about putting these in a residential neighborhood. I mean, I've gone to people's houses before, and during times that the turbines are not spinning, you can actually see some songbirds resting on top of it or on the blades itself. Have small birds been impacted by small wind turbines? I'm sure they have been. I don't have any figures on it because, like I said, there hasn't really been any research in that regard. But compared to the utility scale and the types of birds being impacted, the impact of these turbines would probably be very minimal. Some other siting challenges, I mentioned a little bit about some other environmental concerns, specifically the indirect impacts on wildlife. Do these turbines affect animals in more regards than just animals getting hit by the blades? And this could be due to, this considers things like habitat fragmentation from having to construct roads or transmission lines or the path to the turbines themselves. Does this include things like bird predators, other things other than avian life? Is there any effect on things like that? I know there's one concern, and it's not just in the operation of the wind farm, but especially in the construction is where a lot of the other this habitat fragmentation and other things come into effect. There's a wind farm, I think, somewhere in Virginia where one of the issues right now is a consideration is that the area that they're looking at developing is supposed to be home to a endangered species of salamander, and construction could very seriously impact the habitat of that salamander, and that is not something that we want to happen. So that is a major concern for that project, whether that project could move forward or not, depending on how the research on that comes to light. Other things include, do the wind turbine or wind farms or wind turbines affect property values? This is a concern I've heard a lot. Lawrence Berkeley National Laboratory did a study in 2009 on this regard, where they sampled about 7,500 different home sales nearby various wind farms across the country. And according to their report, they did not find any significant impact on existing or new construction of wind farms as a determining factor for the price of the sales of the home. And that's the only official study I could really find on, or have found on, property values. It seems to signify that they were unable to find no real impact in their study. Transmission lines are a very big concern of where you're going to site a wind turbine. Typically, in the industry, I believe it's if you don't have a transmission access within 10 miles of your wind facility, you're probably not looking at a good spot because it's going to cost a whole lot of money to get it wired where it needs to go. So nearby transmission is very important in the selection, especially in this area. Road access is an important factor, especially if you're looking at building on a mountain. If you can't get the equipment up there, it's going to be very hard. And then if there is no road up there already, you have to consider what kind of impacts are we going to make if we have to construct a road. You may have heard things like ice throw. That's the idea that when a wind turbine in cold climates gets icy, it will fling the ice long distances as the blade rotates. That's somewhat of an exaggeration, because once ice starts forming, especially in a lift turbine, onto the airfoils, onto the blades, that ice is essentially going to obstruct the lift and break the lift and keep the turbine from performing efficiently. And if the turbine can't rotate, then it's not going to be spinning, and it won't really spin until the ice begins to melt. So when the ice starts to melt, it's more likely going to fall from the turbine. It's probably not going to be very safe to stay at the base of the turbine during an event like that, but the idea that the turbine is going to be flinging the ice great distances into neighborhoods or businesses is somewhat of an exaggeration. And generally in large facilities, if there's an icing event, the power plant managers will probably be shutting down the turbines to begin with, breaking the lift manually. And then you have to consider things like land use. Is a lot of, particularly in Virginia, a lot of lands are protected, national park lands. You don't want to build in those areas. Out in the offshore considerations, you have to consider things like shipping lanes and military operations. All sorts of these factors go in to where they can and can't build wind farms. Yes?
Sorry, can you clarify the bullet under transmission lines? I'm trying to understand.
I hope I may have got the little alligator symbol in the wrong direction, but that's basically the point I was trying to make with that is that for typically in wind farms, if there isn't a transmission line within 10 miles of the site, it's usually not, it's considered unideal because if it's any farther than that, you have to essentially build your connection to that transmission point, and that costs a lot of money to do that. So that's kind of the break point on average. And I'm going to pass it over to my colleague here, Dane Zammit. He's a data analyst with us, but his expertise a lot relates to offshore. So he's just going to cover a couple slides going over offshore wind for you.
Thank you, Kenny. Well, I'm going to keep this as brief as possible because we're running a little short on time. I'm going to talk a little bit about the major difference there is between offshore and onshore wind. The most important thing is that the offshore wind resource is significantly better than it is onshore, and this is because you don't have all the obstructions like buildings, wind, and even the land mass itself obstructs the wind. And the less complex terrain is the main defining factor behind that. Something that you need to consider for offshore that you don't have to consider is the sea depth. And the sea depth and the seabed geology. What rocks you have, is it sand, is it rocky? How hard are these elements? That is a big factor in your choice of your turbine and particularly the foundation structure. Those 6 pictures on the right-hand side are 6 different foundation structures. And there are basically 3 different categories. There's your shallow, which are the top 2 images. They're basically adaptations from the onshore foundations. The one on the left is a gravity base, and the one on the right is a monopile, which is the most commonly used foundation structure in the offshore market to date. The ones in the middle are called transitional depth foundation structures. Those are adaptations from the oil and gas industry. On the left, you have your tripod, which is essentially a monopile, which is driven into the seabed. So you have to basically hammer your foundations into the seabed using a special barge called jack-up barge. These vessels, they're mostly available in Europe, so and in the Gulf. So getting them to Virginia would be very expensive. Renting these vehicles costs probably $10,000 a day at least, if not more. And the picture on the middle right is called a jacket foundation structure. That's another common foundation structure you use on the oil and gas industry, and it's a foundation structure found a couple of wind farms use those in Europe. The depths are basically between 30 and 60 meters depth. For shallow, it's between 10 and up to 30 meters. And the foundation structures found on the bottom are called floating. So they use basically different, therefore greater depth. So more than 60 meters, it becomes very cost ineffective to put these structures that are fixed into the ground, and they're very unstable. So they look for more floating technologies. There are 3 main schools of thought for floating. There's the spar buoy, which is the one found on the left. It basically uses a large weight on the bottom to balance out the turbine. And on the right-hand side, there's the buoyancy, which basically uses the same principle that a ship would use, to use the area of contact of the entire structure to provide enough lift to keep the structure stable and floating. A key element for wind farms is where these turbines are going to be sited, the layout, Since offshore wind farms are further offshore, usually the nearest grid connection is much farther off than you'd find onshore, which, as Kenny explained earlier, drives up the costs and makes these projects a little more ambitious. A key advantage for going offshore are the many reduced social impacts, particularly visual impacts, noise, and shadow flicker. This is just because these projects are located much further off the coast, so you can't really see them as you would for an onshore project, and you can't hear them, and there are less shadow flicker impacts unless your project is really close to the coast. Offshore wind projects are a lot more expensive, up to 50% more expensive, if not more than that. They're a lot more expensive. Some of this cost is offset by the approved wind resource. You'll generate more electricity. You'll have larger turbines out there, more efficient turbines, and these will kind of offset the cost. When you analyze an average wind farm onshore compared to offshore, it averages out around 30% more expensive, and most of this is actually because the foundation structures are so much more expensive than they are for offshore. And another key difference, even though the project is offshore, often you need to develop the area onshore, particularly the ports, roads, infrastructure. You most likely have to upgrade where you're connecting to the grid or build a new one. So there's a lot of onshore costs as well involved with an offshore project. Over here, there are a few examples of some actual wind farm layouts that have been installed in Europe. The first one is the North Howell wind farm in the United Kingdom. And you can see the basic layout, a basic grid format. You can see where the turbines are connected and where the farm is connected onshore. Basically, where I want to get at with these four wind farms is that they all use different layouts, and that varies from project to project. There's no best layout. It really depends on how the wind resource and other marine factors, such as shipping lanes. It may not be possible to put them as close to space as possible, like the one on the bottom right. You can see a gap in the middle, and that's because the water there was too shallow to get the vessels to install turbines there. And there are different orientations and things like that. So environmental impacts. As this applies to onshore as well, but an environmental impact statement, as defined by the NEPA Act, is necessary to ensure minimal impact to the marine environment. Basically, the marine environment is amongst the most diverse and life-abundant environments you can find in the world, and some of the most important marine environments are sandbanks, mangroves, which you can see in the top left picture. Those are basically trees, coastal trees, which are important habitats for birds to nest. Seagrasses are on the bottom left. That's actually a picture of the Chesapeake Bay, and these are actually probably the most important marine environment because they are an important source of food for a lot of species, an important habitat, and they also act as a natural breaker of the waves. So they also protect the coast from waves and harsh weather. So they protect the coastal environment as well. Coral reefs are also a huge concern. Coral reefs can be found everywhere, including the northern parts of the world. The cold regions are cold reefs, not just tropical. And as we probably all know, these are important habitats for many marine species, including, and the other shallow inlets and bays and sea caves are similarly as important as all those I've described before.
Yes. Have you heard of any instances where they've built a wind farm offshore and had artificial coral reefs around them?
Well, I've read studies where the wind farms, they can act as an artificial habitat for marine life, where certain species would just settle around there, and but it's not there are conflicting feelings about whether that's a good thing or a bad thing. I don't know too much about that. I know there are studies online. If you can look up most of these projects, they have this documentation online. I think North Hoyle has, if you can Google up the North Hoyle wind farm, and they have a publication of their studies. Most of these offshore projects in Europe have these studies, and
so you haven't heard of them like purposely making a habitat for it?
Not purposely, but it's kind of a unintended consequence of these wind turbines offshore, especially these fixed foundations like the monopile, because it's basically a steel structure in the water, and it can act as a natural habitat. Now something like the floating would not be an issue, because there isn't that structure fixed to the seabed. Did I answer your question? Okay. The main concern with birds, bats, and marine life, the primary thing is during the construction phase, mainly due to noise and vibration. And what you would find for the time window, the time frame for most offshore projects is very short, mostly because you do not want to be constructing these projects during breeding season, because this is very disruptive to their life cycle, and it could be very bad, especially if there's endangered species in the area. Another primary, I've talked about this a lot, the destruction of important habitats for birds, bats, and marine life. This is what we do the environmental statements for. There's a lot of planning that goes into this kind of thing, and we also need to consider the impacts during the operations and maintenance phase, whether the cables will have an impact, whether if there's a team going out there to do maintenance, how much of an impact will that have, and other impacts as well. Here are some other impacts, mostly due to marine traffic, things like bunkering zones, military activities, including radar, navigation. It's very important, especially in Virginia, where there's a heavy military activity, to make sure that any offshore wind projects do not interfere with their activities. And the same applies to port approaches and shipping lanes. It wouldn't be a very good thing to design a wind turbine that would be too close to a shipping lane, because there's potential for impact, which would likely cause damage to either the turbine or the ship itself. Nature reserves, the farther away a project is from a wind turbine, the less disruptive it will be towards the endangered species. Fishing and fish farming. Basically, this could be a very important issue, because while the wind farm is there, it's not going to be a great area for fishing, and if it's an important fishing ground economically for the immediate area, this could do a lot of harm to some local businesses and the fishing industry. So these are all things we need to consider in a wind project. Yes, and the archaeological sites, shipwrecks, areas of historical significance, areas that a lot of divers might want to see underwater. boating, yachting, tourism, other recreational activities. And I've already talked about this. The major driving factors behind the cost is the distance to shore, more cabling, deeper waters, larger turbines, the foundation structures. Normally a wind farm would have an offshore substation. Yes?
Well, I'm curious for what's considered ideal at Virginia based on the knowledge we have now. How far offshore would the wind farms be sited, and what's the depth?
Well, BOMER, the Bureau of Ocean Energy Management, they have designated us a number of lease blocks. I think it's around 30 miles off the coast of Virginia Beach, and that is the main designated area for offshore wind in Virginia. Now, the research I've been involved in is a more coastal project, right off Newport News, Suffolk, and the Chesapeake Bay Bridge Tunnel. That's more of a coastal project, more test demonstration, and these depths are probably in the shallow depth range, like 30 meters, so around 50, 60 feet at most. For the near, and I think the Bomer region is probably a little deeper. I'm not sure exactly how deep it is, but not much deeper than that. Yes, and often offshore wind projects will have an offshore substation that you would use to connect your wind farm to the grid, transform the electricity generated to the right voltage for transmission, and yeah, the driving costs to upgrade ports, build roads, and upgrade electrical infrastructure onshore. Okay, that's the end of my presentation. Thank you for listening.